Hi folks, good afternoon. I'm Shankar. I am going to be talking about ISI's deployment guidelines and some design features, and with some emphasis on some of the new features that ISI has got recently. So we will be going through some of the presentation material also. The agenda for the presentation is, as I said, deployment scenarios. We'll be talking about what is L1 only, how did service providers went through historically, and we will go through some of the models that service providers picked it up, and also look at some design considerations and some new features. Under the design considerations, there are a lot of like set overload bit, LSP flooding, and some of the enhancements that we have got for SPF and PRC intervals, and some more design considerations. And under the new features, we'll be talking about route leaking. Obviously, I just want to make sure that I do mention the new features. Some of them by no means are not exactly new features, but I just don't know where to put in, because some of the features have been in existence at least for a couple of years, like MPLS extensions. But I think it will be a good overview for everybody just to go through some of those. So the scope of the presentation, as I mentioned again, is to cover the deployment scenarios, talk about the design guidelines, and cover also some of the enhancements to the routing protocol of ISIs. I've been asked by some of the colleagues, and actually from the NANOG committee also, just want to have a slide on why ISIs. And these are some of the things that I can actually think of why ISIs, is popular, or why it is receiving a lot of feedback recently in terms of the enhancements. Is obviously embraced by the large tier 1 ISPs historically, and also proven very stable, scalable, and with very fast convergence recently with a lot of enhancements. And encodes the packet in TLV format. Obviously, everybody understands what exactly the TLV, and there are some other protocols also use TLV format. And flexible, because of the TLV nature, it is very flexible in extending the protocol in terms of adding new features, new attributes to the protocol. For example, MPLS TE, and also runs directly over layer 2. I intentionally put that one in the last slide, last bullet. But in terms of the importance, anything can fit anywhere. But again, kind of captures why ISI as a slide. This is what I can actually think of as L1 only POPs. If you look at it, every router with the local POPs and then the core are all L1 only, and the level is L1, and the area also is a single area. And so why did service providers went with level 1 only? So it's a newer protocol, early 1990s. Nobody has deployed it. So it's a single level, and operationally also it's a newer experience for the service providers. And because of the single level, all routers are in the L1 and in the same area, flat with a single level. And if you have a change in the topology, every router has to do SPF, because it's a single level all across. And the other things that I can think of, in early 1990s, why did they go through? Because historically, if you look at the protocol itself, ISIs, where every router is just a stub node. So we don't have what's called as route leaking. So they just don't want to have suboptimal routing. So we just went with a single level. And also, if you run, say, L1, L2, then you have 2 instances of the database and 2 instances of SPF, more churn. So the other reason that I can think of. And also, during those days, it's like AGS in 7000, smaller platform boxes, so can't obviously handle at that time, for a lot of route churn, so with single level. The other scenario that I can think of is level 2 only POPs. In this picture, as I said, all in the same area. So code is level 2, and every POP is also in the same area. If you kind of go to the next slide, here it's every POP is in a different area, still level 2. So from a point of migration, this is obviously more suitable where you have a core and every POP is still a level 2 but is in a different area. So later on, if you want to bring a level 1 only, you can just bring the local POP, and it's easy to migrate for hierarchical design. So this is around mid-1990s, and there are ISPs still actually running level 1 only. So I'm not saying here, like mid-1990s, all of them went to level 2 only, but there are significant number of providers went to level 2 only. And the rough approximation of number of routers are 800 to 1,000. And the SPF computation, we have done several convergence tests, about up to 1,200 routers plus or minus about 150 milliseconds. And most of the links into the core are OC12 to OC192. And as I was mentioning, as the network grows, it's easy to bring the L1 only POPs for easy migration. And since it's a single level, it's the same rule applies like level 1, level 2, it's a single database. This is the slide here. I'm not saying the Cisco recommendation, but this is a typical optimized configuration that service providers have embraced in configuring ISIs. There are some of the configuration values that I will be going through later on in terms of the caveats, plus also will be covering what exactly they mean under the design guidelines or under the new features. So set overload bit is one for sure we will be covering, and max LSP, max refresh, and then which is LSP refresh. I apologize for the spelling mistake there. LSP refresh interval, and SPF interval, PRC interval. And we will also be talking about route leaking during the process. We'll be talking about metric style wide, and obviously the hollow padding. This is the newer architecture in terms of the hierarchy with the route leaking. What I'm saying with this picture here is you have a core, which is level 2 only, and you have this, individual POPs, where each POP is actually a level 1 only, connected to the edge of the POP, level 1 and 2. So you're actually bringing hierarchy. So, for example, if you have a POP 1 on the extreme left-hand corner trying to communicate to the bottom right-hand corner, POP 4, you can configure route leaking and leak the prefixes, because by default, the L1 LSPs will be leaked into the level 2 database, but not the other way around. Like L2 won't be leaking back into the level 1. So if you look at the POP 1 L1 only routers, by default will be leaked into the L1 L2 routers, which are at the edge of the POP, which will be running L2 into the core, comes all the way to the L1 L2 at the POP 4, and since they have been configured for route leaking, they will be leaking those now the L2, since they have it in the routing table, into the L1 database, so that the L1 only in POP 4 can take advantage of best exit, to avoid suboptimal routing. We will be talking in a greater detail when we do go through the route leaking. So that's pretty much what I explained. Within a POP, all routers in a separate area, L1, L2 routers at the edge of the POP. So they have L1 adjacency going into the POP, L2 adjacency into the domain, into the L2 domain. And going back to the previous slide again, here I have depicted every POP in an area by itself. That means we have a concept of ATT bit, which is attach bit, where if I'm an L1, L2 router, if I'm connected to a different router, then I will be, which is in a different area, I'm going to set the ATT bit in the L1 database. So that is what exactly I'm saying here on the fourth bullet, which is all L1 routers in a given POP will receive the ATT bit from the L1, L2 routers at the edge of the POP. Along with when you do the route leaking, you have you are actually getting the individual prefixes with the metric associated. So you won't get into the problem of suboptimal routing. And the recommendation is when you do the route leaking, always use metric style wide, which is the new extensions to the ISIS protocol. This has been around for at least a couple of years. I'm still going back to this particular slide here, where I did mention every POP is in an area by itself. They can be in the same area. That means the whole domain can be in the same area, and we can still do the route leaking, because route leaking is independent of whether my POP is in a single area or not. That's pretty much I have these slides on the deployment scenarios. Let's go through some of the design considerations in deploying the protocol and set overload bit. So here I will be going through a bunch of features that the protocol has. So historically, when you look at the ISO 10589, with where they actually set the ATT bit, the overload bit, to say I'm busy, like if the router is churning. But since then, we actually have modified to say, where BGP is not converging. So we will be going through. And if I set the overload bit, I can be used as a transit router because I'm busy. I'm telling everybody, hey, don't use me. And the color-coded one above that, which is connected IP prefixes, still reachable. That means if I'm overloaded, I'm telling everybody in my LSP database, and I'm flooding it to everybody, and saying, hey, don't use me because I'm still coming. I'm still learning the routes. But during the process, my directly connected IP addresses are still reachable. But you may get into a problem where if you have MPLS traffic engineering tunnels, and if you have a tail end router, and for some reason, if you have a TE tunnel goes down, or if TE tunnel stays up, because your directly connected prefixes are still reachable because you have it to the loopback address, but anything which is downstream is not reachable. So it's kind of black holing the traffic, which is anything behind. So that is where I'm actually mentioning the connected IP prefixes may change. Like if I set the overload bit, even the directly connected IP prefixes shouldn't be reachable, if the application is MPLS traffic engineering. Let's take an example here. R1, R2, R3, R4, R5. Assume router 5 actually set the overload bit. Then what's going to happen? Assuming every link of every path is the same cost, it's obviously going to go through the longer path. So when R1 actually computes the shortest path tree, it will find that R5 has the overload bit, so R5 cannot be used as a transit. So the path is going to be now R1, R2, R3, and R4 to reach R4. And some of the reasons, as I mentioned, where we can actually, and BGP is still churning up, the second bullet, where I have a maintenance window, I booted up the router and it has eBGP sessions and still learning to reach the BGP reachability addresses where IGP converged fast. So you don't want to have the router to black hole the traffic, so it can set the overload bit. That's pretty much what I mentioned, specifically used by the service providers in terms of the BGP. So this is a configuration example where we actually set the overload bit on startup and number of seconds. What actually happens is by default, ISIs will wait for BGP to tell it, which is like 10 minutes. If it hasn't received for some reason a notification from BGP within 10 minutes, it will clear the bit. But BGP by default should be announcing, within 2 minutes. So the option is wait for BGP. LSP flooding. It's a second feature where we can, the main emphasis is actually the last bullet. The point one is ISO 10589 states the LSP flooding on a LAN should be limited to 30 LSPs, but on a slow speed, anything which is less than 2 meg, it may be too much. So you basically want to control the LSP flooding. So the configuration option via is ISI's LSP interval. So similar to EIGRP, where we don't use the complete bandwidth on the interface. So by this configuration, ISIs will be only using 50% of the bandwidth. The other options configuration-wise, we talked about the LSP interval and then the retransmit interval, which is for the same LSP itself, where we are trying to retransmit. The LSP flooding also can be controlled, the CSNP interval, which is periodic, which is done by the DIS on a LAN segment, so we can control the CSNP interval also. The LSP generation, before we actually flood, we need to generate the LSPs. So we can actually control how frequently the LSPs get generated. So we want to wait, how long, between generating the LSPs. And here is a slide which actually talks about some of the reasons, again, not the complete reasons, but some of the reasons for the LSP generation. So when the adjacency comes up or down, or interface up or down, or redistributed IP routes, or inter-area routes, it's again a lot of reasons, but some of the main reasons are put on the slide. So what exactly happens when you generate a new LSP? So you create a new LSP, install in your link state database, and mark it for flooding, and send your new LSP to all your neighbors. And neighbors flood the LSP further. This is the fundamentals of the link state protocol. So you can actually control this frequency of the LSP generation. Say, for example, I have a serial interface and it is constantly flapping, but the contents, there is no reason for SPF, So you just want to control, it's a newer sequence number every time when there is a newer LSP generation, because then there is nothing changed in terms of the topology. So you just want to limit, how frequently you can generate. So, but again, configuring and is also a drawback. So the last, the couple of bullets at the bottom, by default, we actually throttle the LSPs. So we want to make sure you find a compromise between the slower convergence and the faster LSP generation. So you don't want to constantly get into this vicious cycle. This is exponential backup algorithm, recently enhanced. It's been around for a year at least, to where there are enhancements actually done to the SPF interval, the PRC interval, and LSP generation interval. When you actually look at the older implementation, you just have a single SPF interval. Let's take the example of the SPF interval. The same also applies for PRC interval and also for LSP. With the newer, you actually have three options where the first value is actually the maximum interval, how long you actually wait, the maximum for SPF, and then the initial wait between the first trigger and then the first SPF, the trigger and the first SPF. And then the incremental is actually between the first and the second and the third. So let's look at a couple of examples. As I said, it also the SPF interval, the exponential backoff algorithm, actually applies to the other commands also, the PRC and LSP generation. So as I'm mentioning, the first value itself is seconds between the consecutive SPF, which is the maximum, which is usually a number of seconds. And then the second parameter, which is B in this case, is the initial wait between the trigger and the first SPF. And the third parameter is actually the minimum time between the first and the second and so on, which is actually in milliseconds. Here is an example where, SPF interval, if you have configured for tens, 100 and 1000. As I said, the first parameter is always in number of seconds. So we actually, between the trigger and the first SPF, we actually wait, say, 100 milliseconds. That's what actually in the example. And then, say, for example, you got another SPF, which is second SPF. That is the third parameter actually kicks in, which is 1000 milliseconds, which is a second we wait before we do the SPF. And so on, where the next time is actually 4 seconds, and then the 8 seconds, and then eventually it will hit the 10 seconds. And if there is a subsequent SPF, we actually wait the maximum for 10 seconds. The advantage of this exponential backoff is you are actually pacing how frequently you do. Also, you react very fast in the beginning, but at the same time, if it is recurring constantly, you pace your SPF interval. So when the network calms down and when there are no triggers for 2 times the minimum interval, which is in this case, since we have configured the very first value for 10 seconds, we will go to the 20 seconds in this example before we actually go back to the fast behavior, where again the parameters B and C will kick in. It's the maximum interval. I apologize. Yeah, it is the maximum. And as I said, the same syntax for the PRC interval and LSP generation interval. Whereas before the backoff algorithm, when you have only one parameter, which is SPF interval, hit enter, which is with the Cisco CLI, is actually the minimum. So here it's kind of the upper bound. The other feature, this hollow padding also has been around, but in terms of the design guidelines, it needs to be used carefully. And by default, we actually pad to the fullest MTU. And everybody knows why we pad to the fullest MTU. We don't want to get into a problem where when we are actually discovering the neighbors, we send the hello packets, which are hello packets are very small packets. But once you form the neighbors, when it comes to the flooding of the LSPs, where we actually flood the LSPs have to be constant size. And you don't want to get into a scenario where on a point-to-point link where between 2 routers, the MTU is not matching because hellos are smaller. You didn't even get into a scenario to figure out the MTU of the interface. But when you actually flood the LSPs, the MTU has to match, and during that time you get into problems. So by default, the protocol itself usually flood during the neighbor discovery itself to the fullest MTU, so that if there is a problem, it doesn't even form the adjacency. You probably see the same behavior with the other link state protocol also, where actually you get into the problem and get stuck in XDOT and exchange with OSPF. So this is like way back, like in early 1990s. But if you look at the newer interfaces, newer deployments, you have POS interfaces or GIGI interfaces, with the larger MTU sizes, and if you have authentication turned on, service providers came back and said, hey, yeah, this is good, but we don't have a real need to pad every packet, because obviously it's inefficient use of the bandwidth and may use significant number of buffers. And obviously when you do the authentication is turned and computed on the entire length of the packet. That means the router has to churn extra CPU cycles. So you can actually turn it on or turn it off, either globally on a multi-point or point-to-point interface basis, or per individual interface basis too, which is no ISIS hollow padding. The database timers, these are some of the default values. By default, the max LSP interval is 20 minutes, and then the refresh is usually 15 minutes, which is 900 seconds. I have a slide previously when I talked about the L2 only, where I said some of the parameters we'll be talking. We already covered the overload bit, and the max and refresh intervals actually can be bumped up to the 2 to the power of 16, minus 1, which is about 65,535, or the refresh interval, which is lesser than the max interval. So the value actually comes about 18.5 hours, 18.7 hours. What I'm saying with this slide is, yes, the high lifetime values are good, but needs to be used carefully, because if you have some information in the database which is stale information for some reason, it takes longer to flood because you have configured for the max age. So using the high values may result in keeping obsolete information in the database for more than needed. So as long as we do know the drawback of actually having the high values, but the high values by itself are good, but just remember as a caveat. This is a case where if you have point-to-point interfaces between two nodes, like directly connected, what I will be doing, whether I will advertise both the interfaces that I'm connected to my downstream, to my neighbor, to my downstream neighbors. This is basically non-advertisement of parallel adjacencies in the LSP. So when you are actually building an ISIS LSP, all adjacencies by default are actually inserted into the database, and so parallel adjacencies may therefore be included and advertised. But there is no reason for it to be advertised. That's all I'm trying to mention here. So the advantage of not actually advertising the parallel adjacency is you have a smaller package, smaller LSPs, and the SPF calculations will be more efficient. Let's take an example figuratively. Say, for example, router A is connected to router B. And here, say you have two interfaces between A and B, which is 5 and 3. Is it necessary for A or B to advertise to downstream routers, say, for example, CRD, both the links? In a way, it is by default we do advertise, but there is no need, because when actually a packet comes into, say, for example, A, either way it actually is going to look into the forwarding table and does know that there are two links, and based upon whatever the metric, and if there is a load sharing, then it actually can do the either equal load sharing or unequal load sharing. So it's either way, it's local to the router. So in terms of advertising to the downstream, there is no need. So just kind of, you can I don't know whether you can see the PowerPoint thing, but basically I'm just highlighting the IS value 5B, where there's an algorithm where you don't advertise the higher cost link, or the lower cost link. But in this example, I just picked up the higher cost link where we are not advertising to the downstream neighbors. This is the last part of my agenda where it's new features. Any questions so far? The caveat with moving forward with the new features is, as I said, some of the features are in existence for a little while, like dynamic hostname, but I will be covering just so that we do cover some of the features that have been around for a little while, but at the same time summarizes all of them at one place. And some of you folks may be familiar with dynamic hostname, but historically where there is no dynamic hostname, that means there is no TLV to advertise. So you have to do CLNS host mappings. And it's obviously very cumbersome. If you have, say, for example, 400 routers, and you are adding the 401, and think about the script that you have to generate and touch and cut and paste on how many number of routers, or even if there is an error. So there is a new TLV actually got introduced about a couple of years back, which is TLV 137. It's documented in RFC 2763, where it actually floods the host names dynamically. So you can actually see show ISIS topology, where you can actually see the host names mapping dynamically. You can, if you want, you can turn it off using no hostname dynamic. But
Can you turn it off on an interface basis?
it's actually per load basis. Yeah. Yeah, it's in the LSP where you actually advertise. It's a good question, but it's a router basis, so you just flood, within your LSPs. Since it is the default behavior is to turn it on. That means it doesn't show up in the config. So the hostname dynamic doesn't show up unless you turn it off. To change the default is to configure no hostname dynamic. If you're running a newer software. No, positive. Yeah. If you are running a newer software with Cisco, you can, but which is whatever the IOS that you have to run, then the hostname is flooded, which is TLV 137, is flooded dynamically. That is why the third bullet I'm saying floods the hostnames dynamically. You don't have to configure. But when I was going through the slides, I just wanted to make sure that you understand. You may come back and hey, if I want to turn it off, so that is why I had. You can turn it off using no hostname dynamic.
Is there any warning if for whenever hostnames are multiply used?
You get the question is if for some reason if you have two host names and if
if two different routers get the same host name with the local config, there is obviously no warning.
Yeah, let me
confuse the operator.
Yeah, let me go through and I will take the questions for sure. Yeah, if you have the dynamic host name, and if you have, for example, CLNS hostname mapping also, CLNS hostname mapping obviously will take precedence. Even though you are advertising and flooding the LSP, it's still CLNS hostnames. The static mapping will take the precedence. Like when for example, when you do the show ISIS database, you just see the static mapping. And you can actually see the static mappings with the show host command, and the dynamic mappings using the show ISIS hostname command. The last bullet I'm trying to say is, for example, during the dynamic hostname mapping, if you change the hostname of the router, it may not get flooded immediately. The likelihood of you changing a router name is very unlikely in production network. So unless the next refresh interval comes into the picture, when you flood the new LSP, then the newer name, if you have changed, will take into effect. That's what I'm trying to say. This is the newer feature again, route leaking. We did mention about a couple of slides previously. The RFC 1195, which is the ISI for IP, defines all routers as stub. That's what we talked about also, like, why service providers went only with, say, for example, level 1 only. So no information is leaked from L2 into L1 database. So hence all routers are forced to route to closest L2. This may result in suboptimal, and we will see some of examples. And this is only IP feature, and it is not a CLNS, because you're only leaking the IP prefixes. So this new feature actually allows redistribution of L2 IP prefixes into L1 and enables level 1 only routers to pick the best path to exit the area. And if you are using MPLS VPNs for PE reachability, where you actually have a loopback addresses, between the POPs, you can actually leak the loopbacks into the local POP, so the routers can actually pick the best exit point. The caveat for the route leaking, it has to be there in the L2 database, plus in the routing table. If you don't have it in the routing table, you won't be leaking it. So that's what I'm saying. Prefixes must be present in the routing table as level 2. Otherwise, no leaking occurs. And same criteria, then L1 and 2L2. When leaking the routes from L2 backbone into the L1, you may get into a scenario where, say for example, you leak from L1 to L2, and then again L2 may leak back into the L1, and then L1 may have a backdoor which may leak back again into the L1. So you have a loop protection mechanism which can be used to detect, which is we'll go through in the next couple of slides, which is actually TLV 135. TLV 135, if you look at the format of the TLV 135, it has an up-down bit. Let's go through starting from the right-hand side to the down. You have L1 only router. An example which has an IP prefix of 10.14 comes to the L1 L2 router, which is which is obviously L1 so far. Comes into the L1 L2, puts into the L2, all the way comes to the L1 L2, which is in the POP. I should have named the routers. And then when it actually leaks, the L1 L2 router, which is at the item number 3, will be putting the up-down bit and will be leaking into the L1 database. Since the up-down bit has been set, it won't be leaked back into the upper level again. So for example, those L1, L2s won't be leaking to the upper level because the up-down bit already has been set. So that's what I'm saying with item number 4. The 10.14.00 will not be inserted into the L2 LSP since it has the up-down bit set. You leak only from the higher level to the lower level, not the other way around. Once you leak from L2 to L1, it has the up-down bit set. And it is a TLV 135, which is equivalent to the TLV 128 in the narrow style, which is IP reachability TLV. Let's take another example. Here at the bottom of the left-hand side, you have a level 1 LSP with IP prefix 10.1.0.0, comes to the respective L1, L2 routers as an L1, and then leaked into the L2. Actually, by default, the L1 will be put into the L2, so it won't be leaked. So it actually goes, if you kind of follow the left to right, the 1 actually is the level 1 LSP, and it goes to the L1, L2 routers, which is a level 2 LSP with IP prefix 10.1, and comes back to the router which is on the right-hand side, L1, L2 router, it won't be leaking back into the L1 because you prefer your own area, which is L1, but it will be sending to the right-hand side L1, L2, which is on the extreme right of the slide, where that L1, L2 will be setting the ATT bit and will be flooding, and will be actually also doing the route leaking and will be flooding into the L1 domain. So that's pretty much what I'm saying. The L1, L2, when it actually receives from the top, it won't be putting back into the L1 LSP because you prefer your own intra area. You can actually do route leaking with the narrow style, which is been referring to TLV128. Then if you are using TLV128, we actually use bit 8. You know, it has like 8 bits. 6 bits actually for the metric, and the 7th bit is actually for internal, external, and then there is the reserved bit, which is 8 bit, is actually used if you are using the narrow style for up-down bit. But the recommendation is always use the wide style for route leaking, which is TLV135, and to configure is metric style wide. If you're trying to configure the route leaking, you may see some caveats in terms of the CLI. So this may not be an issue moving forward. If you're using 12.0s, you know, it has some syntax versus if you're using any other mainline, you know, it's the redistribute command. But with the newer versions, we actually convert the advertise IP command to the redistribute IP command, which is like redistribute ISIS IP, because ISIS is running for IP. Level 2, you want to leak from level 2 into level 1 with an access list, distribute list, which is like in this example is 100. Some of the extensions for the MPLS traffic engineering have been around, but to cover and summarize, I'll just go through some of them here. And for extensions to the protocol, the new TLVs have been added for MPLS traffic engineering. And we did talk about the TLV135, which is metric style wide, where IP reachability, plus also TLV22, which is actually the adjacency reachability TLV, which is IS reachability TLV. And also we have router ID TLV, which is TLV134. The draft that documents these extensions is draft IET of traffic 04. So it has actually went through several revisions. So we are actually at version number 4. The TLV22 has this particular format where you actually have 7, which represents the LSP ID, which is system ID plus pseudonode ID number, and then the default metric, which is actually 3 bytes, and the length of the sub-TLVs, and then the optional sub-TLV length. So if you are actually configuring for metric style wide, the 2 TLVs, TLV22, TLV135, we're just going through TLV22. The TLV22, the optional sub-TLVs, some of them, the draft that we just talked about does mention for like sub-TLVs and the values for the sub-TLVs, the administrative group or IPv4. Some of these are actually flooded when you are running MPLS traffic engineering. And when you enable the interface, and then you have to advertise the attributes of the interface. What's my IP address, or what's my neighbor IP address, what's my bandwidth, what's my maximum bandwidth, what can be reserved. So some of those, and if the T itself has a default metric. And the router ID TLV for the traffic engineering uniqueness to the node itself. So it's a stable address for traffic engineering, irrespective of what actually happening to the interfaces. We can control, because loopbacks is always stable. Makes sense to have a TLV for itself, which is router ID TLV. TLV 135, which has we talked about the up-down bit, which actually has a metric, which is 4 bytes, which is a pretty huge value. If you look at its counterpart is TLV 128, has only 6 bits, which is 63 is the max. That means the link metric or the interface metric is actually very huge value, and has a UD, which is up-down bit. And we mention if you have a sub TLV or not, with a bit 0 or a 1. And then the prefix length, which is actually the IP address length, and then the prefix itself, and the optional sub TLVs. Recently, there is, if you look at the traffic 04 draft, the IETF draft, does not mention any sub TLVs for TLV 135. It does mention the sub TLVs for TLV 22. But recently, the TLV 135 also has received some, actually one more sub TLV, or one first sub TLV got added. It's actually called administrative tag, where you can actually route the IP prefix coloring. That's all I have actually on the TLVs. This fast hellos is another feature where you can control how fast you want to send the hellos, and so we can actually control the hold down time. By default can be limited to 1 second, so which is the command is ISIS hello interval minimal. By this we actually control how frequently we can send. The advantage is reduced link failure because it's faster hellos, and the disadvantage with it is increased bandwidth or buffer CPU usage. And we did talk about the hello padding. So the recommendation is, don't use the hello padding or turn off hello padding if you are actually using the fast hellos feature. This is specific to Cisco implementation, but I wanted to cover what might happen to the ISIS protocol. So I have a couple of slides on DCEF. Everybody is familiar with the switching mechanism and with ISIS. And ISIS as the protocol runs directly over layer 2. Then if I'm running DCEF, and if for some reason CEF got disabled, it's just an example, but ISIS will still be sending because ISIS is running directly over layer 2. So it still has the neighbors on the line card. So you may get into a black holing. That's all I'm trying to say. So you can actually tell now with external overload signaling command, so that on a GSR, which is in the default behavior is DCEF. So if for some reason if it runs into CEF problem, the adjacency also will come down if for some reason CEF got disabled. Here is an example on the route tags. Is the one that I actually was mentioning about, which is the newer sub TLV that actually got added to the TLV 135, where you can actually route the IP prefixes, color the prefixes, or you can actually tag the prefixes. So you can actually do, the control, the routes, redistributed between the area or domain boundaries, or can be used to apply for some policies, where you can actually apply some policies to the ISIS routes. It's similar to BGP communities. Let's take an example. On the extreme right hand, say for example, you have a router A, has two prefixes, say 10.1 or 10.1.10 or 10.1.2.0. The default L1 comes into the level 2, comes to router B, comes all the way to router C. Router C has no way to differentiate between those IP prefixes when it is actually doing the leaking to router D. For administrative reasons, you want to color the prefixes with some value, so route tag, with the new feature will enable. So as I was mentioning, router C doesn't differentiate IP prefixes between the two prefixes because when it is leaking, but you can actually configure, the route tag to differentiate and have a tag value. So router D can apply some policies and take the necessary action. It's part of the draft Martin/Neil. Right now the version number is 2. And as I mentioned, it's part of a TLV 135. The tag itself, when it can be applied per interface basis, or when it can be like you can apply the tag if you are redistributing for external routes, or when filtering between L1 to L2 or L2 to L1, or even on a summary address. Here is an example of the tag itself, where the interface tagging, if you apply on interface, it's ISIS tag. And where you actually apply the X as a value. You can actually see the tag value using the database detail verbose command for the interfaces tagging. Is actually, it's a huge value. I don't have it handy. Yeah, it's a big value. Yeah. This is another extension to the protocol, part of the draft ISIS IGP point-to-point or LAN. If you look at web hosting environments, like if I have two routers, most of the time directly connected going down to a couple of switches. That's all you have on a LAN segment, but by default you have a DIS on a LAN. But if you look at the new model with the service providers, so in a web hosting environment, so even though you just have two routers on the LAN, you have a DIS. So there is a new draft came and mentioned, hey, if I have directly, two routers on a point-to-point on a LAN, there is no need for the DIS. Treat the media as a point-to-point interface. So when broadcast interfaces, for example, Ethernet, FE or a GIGI or a FIDI, used to connect only two routers, tell ISIS to behave as a point-to-point. When you mention that obviously point-to-point interface doesn't have any DIS, no need for CSNP, because every 10 seconds DIS will be periodically sending the CSNPs, which is complete sequence number packets, which is summary of all your LSPs. And also obviously, since there is no any DIS selection, so reduce the number of nodes from the SPT algorithm. Which is the typical topology where you have two routers on a LAN segment. Obviously, there is a virtual node, which is a pseudo node. One of the routers is going to be the DR or a DIS. And by default, when you do actually the SPF doesn't care whether it's a point-to-point or a broadcast. So it's just all links by default for SPF are point-to-point. So in this case, pseudo node actually considers router A or router B as a point-to-point. So take advantage of that, and I have a configuration example also, ISIS network point-to-point, where now if I have, they're treated as a point-to-point interfaces. As I mentioned, there is no DIS, one step less in SPF computation, and no CSNP flooding. It's primarily used, in a web hosting environment. This is part of the MPLS traffic engineering, but again, specific to ISIS. Let's spend some time not looking at the slide, but when you look at the MPLS traffic engineering with ISIS, when you have a traffic engineering tunnel, the TE tunnel where you have concept what's called a head end or a tail end, from the knowledge point of view, or from it's only local to the head end or to the tail end in terms of there exists a TE tunnel. So the downstream nodes doesn't know anything about it, the existence of the TE tunnel. So if the traffic is coming into the head end tunnel, it just sends on this TE tunnel. But the requirement came from the service providers to say, hey, I want to advertise this TE tunnel as a regular adjacency to my downstream nodes, so that downstream nodes can actually do the SPF not only based upon my physical path, but also based upon this TE tunnel, which is advertised as regular adjacency. So basically, it's the ability to advertise the TE tunnels into the IGP, which is ISIS, as a regular link. That means by default we are not advertising this TE tunnel as a link. So the IGP, which treats this as a normal link, and it's called as forwarding adjacency, it's part of the draft. We don't follow the complete draft, but we take a part of the draft because the IETF draft actually has more hierarchy built into it. FA masks the unequal physical topologies so that downstream nodes can do load balancing to the destination node. The bottom line is able to advertise the TE tunnel as a regular link to the downstream nodes. So what happens from the ISIS point of view? LSPs will be put into the ISIS database because I just mentioned this TE tunnel will be advertised as a regular link. That means I have to put into the LSP database, and since it's the TE tunnel, we don't want to send any hellos because there are other mechanisms for sending the hellos. What are the other mechanisms? It could be CRLDP, it could be RSVP, so just to find the liveliness for the tunnel itself. There are other mechanisms to see whether the TE tunnel is up or not. So there is no need to send again another hello on the tunnel interface. And also, the LSPs itself won't be flooded on these TE tunnels because we still flood the LSPs on the physical media. And the last bullet is SPF bidirectional check. Means if I have a head end tunnel and if I have a tail end, tunnels are by default are unidirectional. That means head end to the tail end. You don't have to have a tunnel back. But with this, when you form an adjacency with ISIS or any link state, you have to have, I send a hello, you have to send me a hello, three-way handshake, all that. It's the same concept. That's why you have to have a bidirectional tunnel. Let's take an example. I wanted to make it animated, but it's difficult to do animation with this, with so many routers and arrows and metric values. Either way you look at it, say for example, we start in router E, on the extreme right. I intentionally came up with, this is simplistic topology, but to illustrate FA concept, introduced in the core, say for example, router B, C, D, router F, and router G form part of the core. Hypothetically, it's a simple example. That means on the upper path I have 3 boxes, and then the down, I have only 2. When you look at the MPLS traffic engineering, you have a TE tunnel, like here router D, router F, router G, and router B are actually acting either at a head end or a tail end based upon their role. When they do, there is the downstream routers like router A, router E don't know anything about the TE tunnels. What we are saying is now we want to advertise this TE tunnel as a regular link to router E or router A respectively, so that router A, which is downstream nodes, can actually do the unequal or equal load balancing. because obviously going through the upper path it has a larger and bigger metric, and going to the bottom path is a shorter path. So router A or router E will not know the MPLS-TE tunnel as an additional link. Now it will know as an additional link. So it allows the load balancing on the unequal cost paths and hides the core topology. Like even if I introduce any number of routers, it doesn't matter because it hides the core topology. Just want to stress that FA has a benefit in particular cases, not in every case where you actually want to advertise the link to the downstream as an FA link. And as I said, we only follow part of the draft because the draft itself actually talks about we cannot use the FA to do the LSP hierarchy since there is no TE information on the FAs. The LSP, the draft actually, which is the draft IETF, mentions the FA links also should carry the TE information, but we are not carrying the TE information. But we are just advertising the regular link. Some of the suggested reading that I can think of, just summarized on the last slide, and the 10589 draft, RFC 1195, they've been in existence for almost more than a decade. And we talked about some of the topics in the draft ISIS traffic 04, which is the extensions to the MPLS-TE, and we did talk about the point-to-point adjacencies and the route leaking, which is documented in RFC 2966, and the dynamic host name, which is 2763, and then the admin tags, which is still in the IETF. It hasn't actually went to the IETF working group yet. That pretty much concludes my presentation. I'm more than happy to take any questions if you have any. No questions? Question? Okay.
You were talking earlier about the dancing of the LSP generation.
Mm-hmm.
As some change to deal with traffic links.
Mm-hmm.
Dancing of the seems an indirect method. Why not dance or link say dancing adjacent to bring up something's come down.
On the interface basis itself? Yeah, it's a good question, yeah. You can do that, yeah. But we don't have any, you basically control on the entire router itself rather than per interface basis.
On the overload bit being set for the wait for BGP conversion,
Yeah. Mm-hmm.
It's affected only at draft startup time?
It is affects only, that's where when you actually want to use it. Like, for example, you have an iOS upgrade or a router upgrade, whatever. If the router is booting up, either maybe something happened, router came back up. That is during that time. If it has BGP sessions, you want to tell the router, hey, IGP converges faster. And so everybody's looking at this router to send the traffic to this BGP prefixes, and it still hasn't converged. So yeah, it's during the boot up process. And as I mentioned, the default, the ISIS will wait is 10 minutes for BGP to inform. But by default, BGP informs within 2 minutes. But then you can come back and say, hey, I have 100,000 prefixes, hypothetical, which is true with eBGP peers. 2 minutes is not that enough. But in reality, a lot of times, the router role is just a route reflector, getting some partial routes, not a complete route. So 2 minutes is more than enough. But if for some reason, if BGP has an informed ISIS will clear the bit, within 10 minutes, and will regenerate the LSB without the ATT bit. Any more questions? Any questions on the new features? Point-to-point adjacencies or MPLS forwarding adjacencies? Thanks, guys.